All right, in this set of notes, we are going to be looking at domain and range. But you guys know me, no lesson would be complete without a nice corny math joke to get started. So here we go. Are monsters good at math? Not unless you count Dracula. Ha. All right, I know, it's bad. All right, this set of notes is NotesD, and we're going to look more closely at domain and range. We got a little intro to domain and range when we looked at our NotesC intro to functions, but we're going to dive a little bit deeper in this set of notes. All right, so the first question, we want to find the domain and range for each function. Now, keep in mind that when we talk about domain, we are talking about our x values, and when we talk about range, we're talking about our y values. Okay? Now, when we look at this from a graphical standpoint, for domain, we're going to want to make sure that we scan our graph from left to right. And when we look at range, we're going to want to make sure we scan our graph from bottom to top. Okay. Now, as I look at this first example on the left, the furthest x value to the left that this graph covers is -4. I'm going to write D for domain as we answer this question. And the furthest x value to the right that this graph covers is 5. Now, you've probably noticed there's a little bit of a difference in those 2 points. When we have an x value of -4, you're going to see that the point associated with that x value is an open circle. And the x value at 5, the point that's associated with that x value is a closed circle. Let's make ourselves some quick little notes over here. When I have an open circle, that means that my point is not included, and we're going to use parentheses. When I have a closed circle, that means that my point is included, and I'm going to use a bracket. Okay, so if we look at this example again, on the left-hand side at an x value of -4, I had an open circle, so -4 is going to get a parenthesis. On the right-hand side, I had a closed circle at an x value of 5, so my 5 is going to get a bracket. Okay, so there's my domain, -4 to 5. Now my range, I'm scanning from bottom to top. I'm looking at my y values. So the lowest y value that this graph obtains is at -3. And at that y value, there's an open circle, so I'm going to use a parenthesis. And the highest y value that this graph obtains is 1, and it's a closed circle, so we're going to have a bracket there. Okay. Let's jump right on to that example on the right. Okay. Looking left to right with my domain, I see that the x value furthest to the left that this graph obtains is at -3. Notice that the point that's associated with that x value, -3, is closed, so this is going to get a bracket. Furthest x value to the right is 4, and that also is closed, so it's also going to get a bracket. Now, on my range, the lowest x value that this graph obtains, or the lowest y value that this graph obtains, is -4. Notice that the lowest y value that this graph obtains was not at one of my endpoints, and that's perfectly fine. I've got to make sure that I'm scanning my entire graph when I look for domain and range. Now, another thing to talk about is that there's not actually an open circle or a closed circle at this y value of -4. This y value of -4 is simply part of the graph. It is a point on the graph, so they don't bother to make any kind of extra notation of open circle or closed circle. But because we know that it's included on the graph, it behaves like it would a closed circle. So that -4 is going to get a bracket. And the highest y value that this graph obtains is at a y value of 3. It also is included in the graph, so it is also going to get a bracket. All right, let's check out what happens in the next slide. There we go. All right, in the next slide, we have two graphs again. In the first one on the left, the x value furthest to the left as I scan from left to right is going to be -6. There's a closed circle associated with that x value of -6, so we're going to get a bracket. And now, as we scan my x values further and further to the right, this graph actually continues to go further and further and further to the right as well. So although it's not written down here, it's implied that this graph continues. Okay, so you're going to find that as I continue on this graph, my x value is going further and further to the right. So in this case, my x value furthest to the right is going to be infinity. Now, we can never actually get to infinity, or negative infinity for that matter. So infinity and negative infinity are always going to get parentheses. Always, always, always. Okay. Let's look at the range now. The lowest that this graph is going to go, so again, because this graph continues to go further and further down on that right end behavior, my lowest y value that's going to be obtained or get closer and closer to is going to be negative infinity, which automatically gets that parenthesis. And then the highest y value this graph obtains is 1. And that value of 1 is included in this graph, so it's going to get a bracket. Now, we've got something new going on this right-hand graph. We have what's called a vertical asymptote. So right here, where I have this red dotted line, this is what's referred to as a vertical asymptote, okay? That vertical asymptote happens at an x value of 1, okay? Now, this is going to affect my domain because as I scan this graph from left to right, my graph is never going to touch that vertical asymptote at x equals 1. So what we're going to find in this situation is that I actually end up with two different pieces for my domain. When I look to the left of the vertical asymptote and I scan from left to right, I'm going to find that my graph goes all the way to negative infinity and then it comes up to 1. Now, this is a similar situation to the last graph where this is just going to keep going and going and going. As it does that, my x values are going further and further to the left, so we're going to go towards negative infinity. Now, on the right-hand side where we look at 1, because there's a vertical asymptote there, my graph is never actually going to touch 1. 1 is not going to be included. So that 1 is going to get a parenthesis. So anytime we have a vertical asymptote, that vertical asymptote x value is always going to get a parenthesis. Now, we've got to pick up on the other side of that value of 1. So we're going to have 1 with a parenthesis again. And this time we're going all the way to positive infinity. So as this graph continues on further to the right, that x value is just going further and further to the right towards infinity. Because it's infinity, we know that it's automatically going to get a parenthesis. Now, because I have two pieces here that I'm looking at, I have to make sure that I always join them with the union symbol. All right, now let's look at range. The lowest that this graph goes is going to be all the way to negative infinity because my y values are going to get lower and lower and lower as my graph goes down at that vertical asymptote. And the highest that this graph is going to go all the way up to positive infinity because as the graph over here on this left end behavior goes up, my y values are simply increasing. So I'm going to have a range of negative infinity to positive infinity. All right, now those first couple examples we explored through graphs. We also need to figure out what's going to happen when I look at domain from an algebraic standpoint. Okay, so when domain is not specified, okay, we say that domain when not specified is all reals that produce real numbers. Okay, so essentially, we're going to assume that domain is all real numbers unless there's a problem, or you're going to hear me refer to it as a bad thing. So we'll talk about what those bad things are in just a minute. So what we're going to do is we need to find values of x that do not produce real numbers. So we are looking for the bad things. And I know that does not mean much to us right now, but we are going to get more into that. Okay, so let's go through and explore a variety of different types of functions. And as we go through these, I'll introduce to you what those bad things are. All right, so polynomials. Okay, a few examples of polynomials. We might keep it simple and just say f of x equals 3. We could have g of x equals negative 2x plus 1. Another example might be h of x equals x squared minus x minus 5. Anytime we have a polynomial, we are going to find that our domain is all real numbers. Okay. We're able to write that in interval notation from negative infinity to infinity. We're also going to come across what's called set builder notation. With set builder notation, we always start with a brace. We specify what the variable is. Then we write a little vertical line that means such that. And then we put our condition. So this would be that x is contained in all real numbers. So this little curvy e here means contained in mathematical symbols. And that r with the two vertical bars is real numbers. So you probably just learned some new math notation in there. And then we're going to close it with a brace. So polynomials are our friends. Domain is all real numbers. Okay. Absolute value functions are also the same. For example, if I had f of x equals the absolute value of x plus 1, maybe minus 3, I can plug in any x value I want and I will get out a real number. So this one also has a domain of all real numbers. So polynomials are our friend, absolute value functions are our friends. Okay. Let's look next at odd root functions. So when we talk about odd root, we're talking about cube root, for example. That's going to be your most common odd root. But the index can be any odd number. So we might also have something like the fifth root of the quantity x minus 2. Okay. I can plug any number I want, any real number I want, into an odd root, and I will get out a real number. So for example, if I wanted the cube root of 8, it would be 2. If I wanted the cube root of negative 8, it would be negative 2. So the odd roots also have a domain of all real numbers. Where we're going to come into our first bad thing is with even root functions. Okay, with even root functions, most common one you come across is just that generic square root. With even root functions, we have to make sure that x is greater than or equal to 0. whatever expression is underneath that radical has to be greater than or equal to 0. Okay, so let's write set expression under radical greater than or equal to 0 and solve. Now, square root's most common you're going to come across, but it could also be a 4th root, a 6th root. But this is really our first bad thing. Our first bad thing is that we cannot have a negative number under an even root. Okay. This is a situation that we'll get into later where we have imaginary solutions, but for our purposes at this point, we're just going to say that there's no real solution. So that's the first bad thing that we're coming across. All right, now the other issue that presents itself is when we have a rational function. So for example, a rational function is just a ratio of polynomials. A common one would be something like f of x equals 1 over x. But we could get fancier here and say x squared minus 4 over 2x squared plus 3x minus 5. Okay, that's just a ratio of polynomials. Now, the key with rational functions is that we do not want the denominator to be 0. That's going to be our second bad thing. Okay, so what we need to do in this case is we need to set the denominator equal to 0 and solve. When we do this, though, these are going to be the values that you cannot have, because if I were to plug those x values back into my function, those are the numbers that are going to make my denominator 0, which is what I cannot have. So these are the values that I cannot have. Okay. So let's kind of just simplify this as our second bad thing, but we can't have a number over 0. So as we go through some examples now, basically the assumption is going to be made that our domain is all real numbers unless one of those bad things presents itself. So we are looking for, is there a square root or an even root? And is there a fraction? If one of those two situations presents itself, then we got to do a little extra work. Otherwise, we're going to assume that the domain is all real numbers. So here we go. First example. We want to find the domain for the square root of 2 minus 3x. And once we find it, we want to write our answer in set builder notation and interval notation. All right, so as I'm looking at this problem, what's going through my mind is I'm asking myself, is there a square root? And is there a fraction? I immediately say yes because I see that square root. So that means that what I need to do is I need to take what's underneath the radical, 2 minus 3x, and I need to set it greater than or equal to 0. All right, let's solve it. So I'm going to subtract 2 from both sides. I'm going to get negative 3x is greater than or equal to negative 2. Divide by negative 3. Now remember, when you divide by a negative with an inequality, we got to flip that inequality symbol. So I'm going to get x is less than or equal to. And now a negative over a negative is going to give me a positive 2/3. Now, the solution to this inequality we just solved is going to lend us real nicely to that set builder notation. We're going to start with a brace. We're going to write x such that, and then we simply write x is less than or equal to 2/3 and close with our brace. So this is my set builder. Now, when I go to draw my, when I go to write my interval notation, for me it's always helpful to have a quick sketch of a number line. I'm going to put 2/3 on that number line, and it has less than or equal to. So at 2/3, we're either going to put a closed circle, or you might also want to put a bracket, and we're going to shade everything to the left of that. This sketch just gives me a nice visualization to write my interval notation from. So all the way to the left where I have shaded is going to be -infinity, and then I'm going to come up to 2/3, and at 2/3, because it's included, it has that equal to, I'm going to put a bracket. This is my interval notation. Okay, now in the next example, I'm going through the same thought process. I'm asking myself, is there a square root? No, there's not, so I'm off the hook with that one. Is there a fraction? Yes, there is. So I need to take this denominator and I need to set it equal to 0. So x squared minus 9 equals 0. And now I need to solve for x. We have some options here. I personally would look at this and I see that it's a difference of perfect squares, so I would factor it. X plus 3, x minus 3. You might also be tempted to use the square root property, which is fine. If you use the square root property, just make sure you remember that plus or minus, because this is going to give me two solutions. Got ahead of myself there. I'm going to get x equals -3, and I'm going to get x equals +3. Keep in mind, though, that these are the values that if I plug them in would make my denominator 0. So these are the values that I cannot have. So as I go to write my set builder notation, I'm going to have x such that, and now I'm going to write x does not equal -3, 3. Okay, so there's my set builder. Now I'm going to sketch myself a number line again. I'm going to put -3 and 3 on that number line. Remember, these are the ones that I cannot have, so these are going to be open circles, but everything else is fair game. So everything else on this number line is going to get shaded. So as I write this in interval notation, I'm going to have -infinity to -3. I'm going to have -3 to 3. And I'm going to have 3 to infinity. And each of these pieces need to be joined with a union. That's my interval notation. All right, here's my next one. I have h of x equals x cubed minus 5x squared minus x plus 1. Same thought process. I'm asking myself, is there a square root? No, there is not. Is there a fraction? No, there is not. So guess what? This one's a polynomial. This one's our friend. We can right off the bat say that this has a domain of all real numbers. This one makes us happy. Okay, so set builder would be x such that x is contained in all real numbers. Interval notation would be our -infinity to +infinity. So that one's a nice, easy one. All right, next one's absolute value. We've got f of x equals the absolute value of 3x minus 7. Same thought process. Is there a square root? No. Is there a fraction? Nope. So, guess what? Same thing, all real numbers. X such that x is contained in all real numbers, or -infinity to infinity. All right, is there square root? Nope. Is there fraction? Yes. So first thing we need to investigate is when does x squared plus 1 equal 0? Now, this one won't factor for us like the previous example because it's not a difference of perfect squares. Notice that this is a sum. So some of you might be tempted to go ahead and try to use the square root property. That would give us x squared equals -1. But what's going to happen when I use the square root property? I'm going to get plus or minus the square root of -1. And that's one of my other bad things. That's not going to produce a real number for me. So go back and think about this equation. If I have x squared plus 1 equals 0, if I square a number, it's either going to be 0 or positive. And then if I add 1 to that, there's no way I'm going to get it to equal 0. So this equation actually has no real solutions. So, although I had on my radar that this was potentially a bad thing because I didn't want the denominator x squared plus 1 to equal 0, it turns out that x squared plus 1 never can equal 0 with a real solution. So this rational function actually has a domain of all real numbers. So x such that x is contained in all real numbers, or -infinity to infinity. All right, number 6. Number 6 says h of x is the quantity x squared plus 4x minus 2 over the quantity x cubed minus 6x squared plus 5x. So, do we have a square root? Nope. Do we have a fraction? Yes, we do. Ding, ding, ding. So, we need to take this denominator and set it equal to 0. Now, notice that I don't care about the numerator at all. Only thing I'm worried about here is the denominator. All right, let's see what we can do to solve this equation. X cubed minus 6x squared plus 5x equals 0. Notice that all three of those terms have an x in them, so let's factor that x out. We'd be left with x squared minus 6x plus 5. Now, don't forget to copy over that x in the front, and it looks like we're going to be able to factor x squared minus 6x plus 5. So this would give me x and x, and we want to multiply to 5 but add to -6. So let's do -1 and -5. All right, let's set each factor equal to 0. And this is going to give me 3 solutions. I get x equals 0, I get x equals 1, and I get x equals 5. Now again, keep in mind that these are the numbers that I cannot have because if I plug them in, they are what makes my denominator 0. So when we go to write set builder notation, we're going to say x such that x cannot equal 0, 1, and 5. Okay. Now, for our interval notation, let's sketch out that number line again with 0, 1, and 5. And remember that I cannot have those values, so we're putting open circles there. Everything else, though, is fair game. So that's going to give me -infinity to 0, 0 to 1, 1 to 5, and 5 to infinity. And each of these intervals need to be joined with the union symbol. All right, last example, number 7. Whoops, I went too far. Number 7 says that f of x equals 1 over the square root of x minus 5. Do I have a square root? Yes. Do I have a fraction? Yes. So I've got two bad things in this problem, so I've got to make sure that I'm taking care of both of them. So normally, if I have a square root, I'm going to take underneath that radical and set it greater than or equal to 0. But because it's on the bottom of a fraction, we know that this cannot equal 0. So we're taking that equals part away, and we are just going to solve x minus 5 is greater than 0. So we had to combine both of those bad things into one. All right, let's solve it. We add 5 to both sides, and we get that x is greater than 5. So set builder, we get x such that x is greater than 5. Let's check out our number line real quick. Notice there's no equal to on this, so we're getting an open circle. And because it's greater than, we're going to shade to the right. So the interval we're looking at is 5 with a parenthesis to positive infinity. And that's it. If you have any questions, please reach out to me and be proactive in getting the help that you need. Otherwise, I hope that this video helped you out in understanding domain and range from a graphical and an algebraic standpoint. Have a wonderful day.